Well, we could get y by itself, and it would be something like y equals 2/3 x minus 17/3. What kind of graph does that give us? Y equals mx plus b. What is that thing? Yes. It's slope-intercept equation of what? A line. These are lines. So what we're working with in this chapter has to do with equations of lines. So what we're going to be graphing is lines. And we've had some practice already graphing lines. Now when we talk about we're solving a solution, is a point. And what we mean by a point is an x and a y, coordinates. That makes both equations true. And what we mean by makes it true is if we plug in x and y here, we should get negative 17. And when we plug x and y into the second equation, we should get negative 8. So you might get a question that says, is 2, negative 7 a solution? And what this question is asking us is, well, plug it in. And see if it works. That's what they're telling us to do. That's how we test if something is a solution. So let's plug into this first one. I'm just going to put a 1. I'll say this is equation 1. 2 times 2. This is x and y. 2 times 2 plus 3 times negative 7. There's my x and there's my y. Well, that is 2 times 2 is 4. 3 times negative 7 is minus 21. And 4 minus 21 is negative 17.
Could I also suggest that you can use parentheses if that helps you organize things? You'd have parentheses after the first two to put
Here?
right there, yep.
And here?
Yeah.
Okay.
Because then your 2 is taking the place of x.
Okay.
Or y.
So that's our first equation. It works in the first equation. In order to be a solution, it needs to work in both. That's why I underlined both here. So in the second equation, I'm going to say 3 times 2 plus 2 times negative 7. Well, 3 times 2 is 6, and 2 times negative 7 is negative 14. 6 minus 14 is negative 8. So it works in the first equation, and it works in the second equation. That means it is a solution. Well, if we're graphing, today we said we're going to solve these systems by graphing. If we graph two lines, what's going to happen with those two lines when we graph them? Aren't they going to make an X shape? They're going to cross somewhere? When we're solving a system by graphing, we are looking for where the lines intersect.
I just want to say that this is the first day of a new chapter. Your electronics should be put away. They should be put away every day, irregardless. We're up here teaching you guys things. You should have your phones away.
Yeah, that I kind of mentioned about the doing the same thing and getting the same results thing. Okay. Solved by graphing means we graph the lines and find where they intersect. And when we say intersect, we just mean where they cross. They're going to cross at some point with an x coordinate and a y coordinate, and that is going to be our solution. All right, so let's look at some examples. Let me get my graph paper here. All right, so our first example. And these graphs shouldn't take a lot of space, so if you draw your axes on your graph paper, you should have room for these. We're going to solve y equals 2x minus 1 and y equals 4x minus 7. Solve by graphing. So let me draw my axes here, make my line a little thicker. There's my y, and here's my x. All right, so we have our equation in y equals mx plus b form. Remember that the number here is the y-intercept. So I'm going to graph this top equation in red. The y-intercept is -1, and the slope is 2. We can think of that as 2 over 1. So to get another point, I'm going to go up 2 and over 1. And if I want another one, I'm going to go up 2 and over 1. And I'm going to draw my line here through those. And there's my nice line through those points. For this line, I'll graph that one in green. The x-intercept is -7. Let's see, 1, 2, 3, 4, 5, 6, 7. I got down here low enough. And the slope is 4. So to get another point, I'm going to go up 1, 2, 3, 4 over 1. Get another point, 1, 2, 3, 4 over 1. And I might need to extend this one a little bit. So I'm going to graph that. Like so. And I'm going to extend the red one a little bit. Like so. And it looks to me like they cross right there. And that point would be 1, 2, 3. 1, 2, 3, 4, 5. That's where the two graphs cross. That would be my solution. I can check my work. I'm going to go down here and check. We don't always have to check, but I just want to show that we can check our work. We're going to plug in x in the first equation and see if it gives us y equals 5. So 2 times 3 minus 1 is 6 minus 1, which is 5. That's what we're supposed to get when we plug in x. And for the second equation, 4 times 3 minus 7 is 12 minus 7, which is 5. All right, questions on that example? Okay, let's look at another one. We'll do a word problem this time. Let's say you have a puppy and it weighs 5 pounds and it grows at 1/4 pound per month. So it gains 1/4 pound a month. And we have another puppy. And it weighs 4 pounds. And it grows, growing a little faster, eats a little more maybe, at 1/2 pound per month. We want to know when will they weigh the same. Well, we're going to set up a system of equations here. So for puppy 1, let's say that, let me erase this. I'm going to say x equals months and y equals the weight. So the puppy's weight for the first puppy is going to be 5 pounds plus the amount it grows plus 1/4 times x. 1/4 pound times every month that it grows. And I could write that in a more usual way, 1/4 x plus 5. For the second puppy, its weight is going to be 4 pounds plus 1/2 pound times every month that it grows. So I could write that as 1/2 x plus 4. And we want to find where the weights are the same. So we're going to graph these lines and find where they intersect. That's how we're going to solve this system of equations. So let's make our graph. Here my x-intercept is 5. 1, 2, 3, 4, 5. Oh, I need to make this a little taller. And my slope is 1/4. So I'm going to go up 1 and over 4. Up 1, over 1, 2, 3, 4. My intersection is going to be up here on my equations. And I'm going to graph that line, connect those 2 points. So, make this so we can read this. Let's undo that. Make that dark. Now I'm going to graph the second equation. Here the y-intercept is 4. And the slope is 1/2. So I'm going to go up 1 over 2 and up 1 over 2, up 1 over 2. I'm just plotting some points because I think they're going to intersect right there. There is my intersection right at the 1/2. Right there.
Your first points on the grade.
4. Up 4.
Yeah, you went up 1 over 3.
Yeah.
Oh, I went up 1 over 3 first. Okay, thank you. So let me back up a little bit. Up 1 over 2. There we go. It shouldn't intersect at the 1/2. Or on the 1/2. Let's see. Up 1 over 2 should intersect right there. So there's my intersection right here. And that is at x equals 1, 2, 3, 4. X equals 4 and y equals 1, 2, 3, 4, 5, 6. Y equals 6. So that's the 0.46. X is the number of months, so they're going to be the same weight in 4 months. And they will weigh 6 pounds. They'll both weigh 6 pounds after 4 months. Now if you did something on a quiz or a test where you did what I did at first and went over 3, I've probably maybe not even take any points off of your graph for that because you did everything else correctly. All right, questions there? Same process as we did before. Graph the two lines, find where they cross. All right, let's look at some special cases. Oh, and I want to back up for just a second with a little vocabulary. So on this first graph, when our system of equations has a solution, we say the system is consistent. And that would be true for this first system. This system is consistent because it has a solution. This system is consistent because it has a solution. When a system has a solution, we call it consistent. All right, our special cases. The first one, we want to solve by graphing. That's this whole section is going to be solved by graphing. And I have the system 3y equals x minus 2, and negative 6y equals negative 2x plus 4. Now what I'm going to suggest for graphing is that we always put the line in y equals mx plus b form. Get y by itself. That's probably going to be the easiest way for us to do our graphing. So for this first line, I have 3y equals x minus 2. I want to get y by itself, so I need to divide everything by 3. Divide everything by 3. And I get, these cancel out. Y equals, I'm going to write x over 3 as 1/3 x minus 2/3. So there's my first equation. For the second equation, to get y by itself, I'm going to divide everything by negative 6. And when I do that, these negative 6's cancel out, and I get y equals negative 2 over negative 6. I can reduce that fraction, divide everything by negative 2, and I get 1/3 x. And 4 over negative 6, I can reduce that fraction, divide everything by 2, and I get negative 2/3. Well, look at that. What's going on there? They're the same. And if we graph these, we're going to get something that looks like this. Negative 2/3 is not quite negative 1. Negative 3/3 would be negative 1. So our y-intercept is about here. And our slope is up 1 over 3. 1, 2, 3. There would be one line. And if I graph the other line, I would get the exact same thing. I would get a point here, graph another point here, and my other line would go right on top of it. That is the same line. Well, in how many points do these two lines intersect in? All the points. So when we get the same line, when we have a graph of two lines that are right on top of each other, literally the same line, we get an infinite number of solutions. And if we think back to way back at the beginning of the semester when we were working on simplifying things and all of that kind of stuff, and we could get an answer like 2 equals 2. This is the same thing. 2 equals 2 is an infinite number of solutions. When it's the same line, we get an infinite number of solutions. Any point that's on this line is a solution to this system of equations. When we get this kind of system, we say it is consistent because it has a solution and dependent because we get an infinite number of solutions. These two are the same thing. So they're dependent on each other. So we say this system is consistent because it has a solution, dependent because they're the same line. And I'm going to back up here again. This system is consistent, and because these two are not the same line, we say they are independent. Consistent because we get a solution, independent because they're not the same line. And you will get questions that say, is the system dependent or independent, da 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 da. So we'll ask you about these things. So this is our first special case. An infinite number of solutions. It's the same line. 2 lines right on top of each other, the same line. And we say it's consistent and dependent. All right, our last special case.
Hey, Mr. Beamer, we have a question.
Yes.
Are they always dependent when they always like match?
Yes. If they're exactly the same, then we say they're dependent. Always. We're going to solve by graphing. Y equals 5x minus 2, and y equals 5x plus 3. Well, what do we see right away that's going on here? They have the same slope. Well, let's graph these things. Same slope, but different y-intercept. So the y-intercept here is negative 2. And my slope is 5. Up 1, 2, 3, 4, 5 over 1. So there's that line. Here the slope is 3. 1, 2, 3. And the slope is 5. Up 1, 2, 3, 4, 5 over 1. So my graph's going to go up here onto my equation. What's going on with those lines? Yes? They're parallel. The lines are parallel. Well, if they're parallel, when are they going to cross? Never. They're never going to intersect. So how many solutions do we get? None. We get no solution. Whenever we have parallel lines, 2 lines with the same slope but different y-intercepts, we're always going to get no solution. Parallel lines, Same slope, different y-intercept, give us no solution. And we call this system inconsistent. When there's no solution, the system is inconsistent. Yes?
If one of the 5x's and negative 5x's left?
Yes. Because then they make like a perfect X shape. The two lines then would be negative 5, yeah. No, not perpendicular, because it's not flipped. So when we get no solution, the lines are parallel, same slope, different y-intercept. No solution, the system is inconsistent. So those are our two special cases. Either an infinite number of solutions when we have the exact same line, or no solution when the lines are parallel. Okay, questions? All right, our homework is a worksheet. Section 6.1, and we're going to do the odds. So let me pass that out for you.